Hello everyone. I'd like to welcome you to my tutorial on PROC SQL programming techniques for SAS users and programmers. I'm Kirk Paul Laflers. As an entrepreneur, consultant, programmer, educator, and author, I have been a SAS software user since 1979. We're going to look at a variety of topics in this tutorial. We'll begin by exploring unique PROC SQL programming techniques. Then we'll turn our attention to join algorithms and execution plans. Then we'll look at fuzzy matching programming techniques and how we can use logic scenarios with case expressions. We'll then take a look at the rules, strategies, and usage of indexes. Then we'll look at the PROC SQL macro interface. And finally, we'll look at the data-driven programming techniques that are available in the SAS software. As with any tutorial, examples are very important to share ideas, to share techniques. In this tutorial, we're going to look at the movies table. The movies table consists of 22 rows or observations and 6 columns or variables. The second table we'll look at is the actors table with 13 rows or observations and 3 columns or variables. In this first section, we will explore unique PROC SQL programming techniques. Let's begin by looking at the PROC SQL SELECT statement and its clauses. The SELECT statement's purpose is to retrieve or read data from one or more underlying tables or views. Although the SELECT statement supports multiple clauses, only one clause is required, the from clause. All remaining clauses are optional and only specified as needed. Some of you might wonder what the order of the select clauses are. I came up with a little jog that will help you remember the order of the select clauses. If you recite, SQL is fun when geeks help others, this should help. Let me show you how. The first letter in each word corresponds to the clause. Here we see the order of the SQL select clauses is select, followed by into, then from, on or where, then group by, then having, and finally order by. So if you can remember SQL is fun when geeks help others, this should help you syntactically specify the clauses in their correct order. Now, what is the difference between these clauses? The execution order is different than the way we specify the clauses. The from clause is the only required clause with the select statement. Its purpose is basically to describe and to collect the data and information, the variable names, variable type, number of rows, and other important information when we're dealing with tables and or views. So it's the first clause that's executed in a select query. The second clause that's executed, if specified, is the into clause. The into clause is used to create one or more macro variables where the values can be used to manipulate data. We'll explore this later on in this tutorial. If specified for subsetting purposes, The on clause is the next clause that's executed. It's used to subset rows of data based on the condition specified, and rows that aren't satisfied by the condition are discarded. If specified, the where clause is the next clause that's executed. Like the on clause, its purpose is to subset rows of data based upon the condition specified, and rows that aren't satisfied by the condition are discarded. If specified, the group by clause is the next clause that's executed. The group by clause takes the rows that were subset with the where clause and grouped based upon common values in the column specified in the group by clause. If specified, the having clause is then executed. The having clause applies the conditions to the grouped rows specified in the group by clause, and any group rows that aren't satisfied by the condition are discarded. Now, the select statement is processed and executed. Expressions specified in the select statement are processed. And finally, if specified, the order by clause is executed. Its purpose is to sort the rows of data in either ascending, which is the default order, or descending order. Now let's turn our attention to the various join types. To illustrate the techniques of each join type, we're going to use Venn diagrams. The first diagram you see here is the inner join, sometimes referred to as the intersect. If we have two tables that we're trying to join, Table A and Table B, the intersect is the highlighted area in cyan or teal. The next join type is the left join. Here we see Table A and Table B. The intersect is highlighted, but also is the left table, which happens to be A. Table A could be classified as the dominant table, the controlling table. So we're going to collect all the intersect, plus preserve all the rows from the left table. The next join type is classified as a right join. Viewing the Venn diagram, we see Table A and Table B, and the highlighted area is the intersect, the common elements between both tables, and then in this case, the B table is the dominant or controlling table. So we're going to also preserve the contents of the unmatched rows from the B table or the right table. And finally, the last join type that I'll discuss is called a full join. A full join should not be confused with a Cartesian product, or in some cases known as a cross join. Yes, it does contain more data, oftentimes, than any of the other join types that we discussed. But typically, if we're looking at Table A and Table B, the intersect, the common elements between both tables, plus the preservation of all the unmatched rows from the left table, Table A, plus all the unmatched rows from the right table, Table B, are preserved and provided in the result set. Now let's take a look at how we can construct an inner join. An inner join, as I mentioned, is going to create an intersect, highlighted here in teal or cyan. If we have the movies table and the actors table, the common rows, the common data between both tables and the key are going to be preserved. In this case, we have PROC SQL no print, Our purpose is to create a table. The table name is going to be called inner join. Since it's a single name, it is going to be a temporary table. So it's going to be called work.innerJoin. And it's going to consist of the select query. Title from movies, rating from movies, actor leading from the actors table, and actor supporting from the actors table. Now this construct that I'm showing here in the from clause, the from clause says movies. I'm going to assign a table alias called M for movies, comma. This is one way to write the inner join construct. And then the second table, actors, with the table alias A for actors. Optionally, we have a where clause, and this is where we relate the title, the key in the movies table, to the title variable or column in the actors table. When they are the same, the intersect is formed. In this second inner join construct, very similar, just a different way to express the inner join or the intersect. In this case, again, we're going to create a table called work.innerJoin. We're going to select the same columns or variables, title, rating, actor leading, actor supporting, from both tables, movies and actors. But instead of the comma in the from clause separating movies from actors, we're actually going to specifically specify the inner join keyword. Sometimes I like to use the inner join keyword opposed to the comma because it succinctly specifies the type of join. So here we're going to say from movies, the table alias M, inner join with actors, table alias A. The where clause is replaced with the on clause. The on clause here says movies.title equals actors.title. The result is going to be the same as the previous example, construct number 1. Just a different way of expressing and specifying the inner join or the intersect. Now let's see how we can construct a left join. In this case, keeping in mind the Venn diagram, the visual itself, our purpose is we want to be able to create a left join type of table. So we'll construct a table called work.leftJoin, selecting the same columns or variables we did before, title and rating from the movies table, actor leading and actor supporting from the actors table. From movies, instead of inner join, we're going to specify left join as our keyword to indicate the type of join we want to create, followed by actors. In this case, the left join keyword says the movies table is our dominant table or controlling table. And then the on clause specifies M or movies.title is equal to actors.title. The end result from the left join construct is we're going to create our intersect plus preserve all the unmatched rows from the left table, the movies table. Now let's turn our attention to the right join construct. Many think, well, if you have a left join construct, do you really need a right join construct? Well, I really think that it's useful because sometimes you want to make sure that you treat the second table as the controlling table or the dominant table. In this case, we could make this join the same as a left join. But I'm purposely not going to do that. I'm going to specify this right join construct where the actors table now is going to be the dominant or controlling table. Take a look at the from clause. The from clause specifies movies. Well, that's the left table. In this case, since we're specifying a right join keyword or right join construct, the movies table is the subordinate table. Now the actors table is going to be treated as the controlling or dominant table. And just like before, the on clause keyword specifies that the movies.title is equal to the actors.title. So the result set of work.rightJoin table is going to contain all the matched rows representing the intersect, plus all the unmatched rows from the right table that have been preserved. Finally, let's take a look at how to construct a full join construct. In this example, we're going to create a table called work.fullJoin. Select the same columns we did earlier, title and rating from the movies table, actor leading and actor supporting from the actors table. Our from clause is going to specify the movies table, and the key word here to indicate the join construct is going to be a full join. This type of table construct, along with the left and right joins, are sometimes classified as outer joins because they preserved the unmatched rows from either the left table, the right table, or both tables. Now I'd like to bring to your attention a process of emulating one of my favorite techniques that I've used in the data step called first dot, last dot, and between. This type of processing is extremely popular in the data step. I worked with SAS software in the late 70s when we only had the data step and into the 80s, before PROC SQL was implemented. And this was the only way we could collect information or data or observations that are treated as first, last, or between. Now, one of the things that I want to show you here is, by definition, it's very difficult to emulate first dot, last dot, and between processing with SQL. But there is some techniques that are available. I came up with a technique a few years ago that would allow me to use SQL to emulate this stalwart approach that users that have used the data step to do this fell in love with. So unfortunately, there's no out-of-the-box PROC SQL solution for handling this type of processing. But we can emulate the techniques with subqueries. So after several years of research and experimentation, I developed a technique using SQL subqueries that emulates the popular data step technique. I'll just show you this technique. Whether you decide to use it, that's up to you. But sometimes some organizations are very SQL oriented. They either don't have the skills of the data step, or their user base is not trained in data step techniques, but they are in SQL. So I wanted to give SQL users, because SQL is such a popular language and it works with so many different relational database management system software, that I wanted to be able to come up with some way of solving this very important problem of identifying first rows, last rows in groups, by groups, as well as the between rows. In this first example, I illustrate how to process by groups that are represented as first rows in each by group. Now what I want to do is I want to show you that I'm creating a table, work.first by group rows. I'm going to select the columns of interest, in this case rating, a categorical variable, as well as the movie title. And I'm going to dynamically create a variable, and I'm going to assign it a value of first row. Now this dynamically created variable is going to be called by group. I'm going to read the movies table and assign a table alias of M1. Then in my where clause, I'm going to say where title equals, and this is the reason why this works, is I'm going to select using the min function, the min statistical function, title from movies. So I'm going to read movies a second time and assign it a table alias of M2, where M1.rating is equal to M2.rating. Essentially, what is enclosed in parentheses there, the subquery select, is going to process that information and then parlay it out to the outer query. And then the results are going to be ordered in ascending order by the movie rating, followed by the movie title. And this is what we're going to get. We're going to create by group processing that represents the first row in each group. So we have 4 distinct rating groups, movie ratings, G, PG, PG-13, and R. This represents, based upon the sort order, the min value for each of the groups. And notice the by group column, that dynamically created variable. I don't really need that, but it's helpful later on, and you'll see why. It's helpful to create because it gives you a better understanding of what was classified as either a first row by group, a last row by group, or a between by group. So this, using the min statistical function or min function, we can collect the first row in each by group. And the by group again is the movie rating. Now let's take a look at how we can emulate the last by group. In this case, you might already be guessing, or you might already know, maybe you've even used this technique. Instead of the min function, we're going to use the max function. Almost everything's the same in this code as from the first by group code emulation, with the exception I'm going to create a table called not first by group rows, but last by group rows. And my dynamically created variable for by group is going to contain the value last row. And in the previous example, we used the min function for title. Now I'm going to use the max function for title. Otherwise, everything is the same. And when we run this code, we're going to see that we have 4 distinct groups, the last row in each group. Now you might say, does Wizard of Oz appear twice? Because Wizard of Oz also occurred for their first by group. And now it's showing in the last by group as well. And that's perfectly fine, because by definition, it is the first and last in each group. And then we see the other distinct groups for PG, PG-13, and R. The last code emulation, because this is important, it's often very important to know what the between rows are. This gives us the ability to know what the first row in each by group is, what the last row in each by group is, but we also might want to know what the rows are that are not first or not last within each by group. And this code gives us the ability to create a table, and I called it between by group rows. We're going to select the columns of interest from the movies table, rating, title. I'm going to create dynamically the min title using the min function and the max function for max title. And I'm also going to dynamically create the by group variable with the value between row. I don't necessarily have to have the min title and the max title, but to make this work and show the results correctly, it is important. Then we're going to group by the categorical variable rating using the having clause, because now we want to use this having clause against the group by, the grouped variable rating, having calculated. Now what is this calculated keyword all about? Well, the calculated keyword allows us, and think back to the order of execution of the query clauses, the select query clauses. The select clauses, and we're defining the min title, the max title, and the by group dynamically on the select. Now the select statement is the first statement that's specified in a select query, but it's the second to last statement or clause that's executed. Consequently, we want to be able to access the contents of these dynamically created variables, min title, max title, and by group. Consequently, we must use the calculated keyword to do so. So having calculated min title is not equal to calculated max title, and calculated min title is not equal to title, and calculated max title is not equal to title, is going to select just the between rows, not the first row in each by group, not the last row in each by group, just the between rows. And then we're going to order in ascending order by the by group variable rating, followed by title. And this is what we're going to get from this code. We see that we have, and if you look at the last column, by group, all says between row, the min title, the max title. So by looking at this, I see that, Wizard of Oz didn't appear here because Wizard of Oz is classified as a first and a last row, but not a between row. It only appears once in the movie's data set or table. But these movie titles for each of these movie ratings are not classified as a first row or a last row. Consequently, they're identified as between rows. Now, it might be useful to be able to concatenate or append the identified first rows, between rows, and last rows together. You don't necessarily have to do this, but I thought, this would be kind of neat to show each one of these three distinct groups concatenated together, row by row. So in this example, I'm going to use the select statement with the variables of interest, rating, title, and by group from each distinct group, the first by group rows, the between by group rows, and then the last by group rows. And I'm going to concatenate them with the union all set operator. Now there are other ways to do this, obviously, but since this is an SQL, a PROC SQL tutorial, I wanted to show you a way to concatenate using SQL. And the union all set operator is going to collect all the rows, including duplicates. And this is what we're going to get. We're going to see all the first rows appear first, all the first rows in the by group category, then all the between rows, followed by all the last rows. Now we did start with 22 rows, and if you look at the row number on the SQL, and I purposely left it in there, you see that there's 23. That's because the Wizard of Oz appears not only as a first row, but a last row. Now we can get rid of that, but I wanted to show you the pluses and minuses with this emulation approach of using PROC SQL to identify first dot, between, and last dot. Now I'd like to show you how we can emulate nearest neighbor processing. The problem is some of the techniques that we may use in the data step are not always available in PROC SQL. Also, PROC SQL performs operations row by row. Nearest neighbor processing is used to identify content that is close to another value. The data step is often used with the lag and lead functions to perform nearest neighbor processing. The data step is a powerful language. But once again, you may work in an environment where there's little or no experience or understanding or knowledge about how to use data step techniques. But there is an abundance of knowledge using PROC SQL or some form of SQL. These techniques can be used within the SAS system to be able to emulate these data step stalwarts very nicely. But let's take a look at something. In the data step, we can use lag and lead functions, but PROC SQL does not support the use of the lag and the lead functions, and consequently produces error messages on the SAS log. So it fails. So if you need to be able to process nearest neighbor type of activity, perhaps we need to come up with an approach. So this approach, and I just am showing you now what happens when I try to use the lead and the lag functions within PROC SQL. Here's code here. I'm going to dynamically create a lag title and a lead title. When I run this, I'm going to get an error. Notice the two errors. The first one says the lag function is not supported in PROC SQL. It is only valid within the data step. The second error says function lead could not be located. What is one to do? Do I just stop or quit and say, well, I guess I have to learn the data step, or I guess I have to write data step code in an SQL-centric organization? Nothing wrong with learning. I love learning, as all of you do too. But sometimes being able to come up with an emulated approach in the desired language, working with data from an RDBMS, is the way to go. So how can we address this problem? This is definitely a problem. It didn't run. The code gave me errors. No results were produced because of the errors. What can we do? Well, here is a way. I don't know if it's the only way, but this is a way that I've used for a number of years. I love output delivery system. ODS gives us the ability to output the results. Now, this approach is going to purposely assign row numbers to our table rows. And I know from an SQL purist, a database purist point of view, that's not always desirable. I've been working with databases since the mid-70s. A variety of databases that in many cases don't even exist any longer. And I've worked all the way up to the current time working with relational databases, including the leading ones on the marketplace. So I'm very well aware that it's not always advisable to create rows of data that have row numbers. But if you want to be able to emulate using this approach, I have to do it. I have to create row numbers. So I'm going to specify ODS output SQL results equals the table, user-defined table, movies with row numbers. And then I'm going to say PROC SQL number no print. In other words, I'm going to purposely turn on the row numbers and write the results to that output, that ODS output statement, movies with row numbers. I'm going to select title and rating from mydata.movies. Then I'm going to turn the number off. In the second PROC SQL, I say PROC SQL no number. And then I'm going to say create table nearest neighbor. So I'm going to create a new table called work.nearest neighbor. I don't necessarily have to drop the row, but I'll do that just to clean things up. As select all columns, select title from movies with row numbers, where row equals m.row minus 1. In other words, we want to emulate the lag feature for the previous title. Whatever movie we're looking at, we want to see what the previous title or the row with the previous title is. This emulates the lag feature or the lag function. Then we say, I want to select the movie title from movies with row numbers, where row equals m.row plus 1. This is going to do a look ahead. And it's going to be able to perform or emulate the lead function. Now, as you might guess, I'm using -1 and +1. Those are values that can be changed. If you want to go back more than 1, or you want to go ahead more than 1, you can change the 1, -1, and +1 to something different. Now, I've hard-coded these values, but they could be specified as parameters into a macro or whatever the case is. And I'm going to then select all columns from nearest neighbor, the table that I created in the create table statement. This is what we get. The results from this, and if we look at the rows in the table, the movies table, title, Braveheart, Casablanca, Christmas Vacation, Coming to America, etc. And if you go over previous title for Braveheart, there wasn't one, so it's blank or missing. The next title says Casablanca. If you go down to the second row, you see Casablanca. Now let's take a look at the row Casablanca. The previous title says Braveheart. If you go to the first row, you see Braveheart. If you go to the next title, it says Christmas Vacation. Go to row 3. There's Christmas Vacation. So the emulated approach to the nearest neighbor within SQL seems to be working. Yes, I had to read the table not once, but multiple times. But sometimes extra processing is necessary to be able to achieve the result that one needs to achieve. And in this case, I needed to be able to use SQL to emulate nearest neighbor processing that I've been using for decades in the data step. But the client told me, we don't want data step code. We are an SQL shop, and we want SQL solutions only. So I had a choice. I can either turn the project down or come up with an approach that will satisfy their desire of having an SQL approach to producing nearest neighbor results. So what are the summary of takeaways from this section? The select statement retrieves or reads data from one or more underlying tables or views. The from clause is the only required clause in an SQL select statement. All the remaining clauses are optional. To help remember the order of the select clauses, simply recite, SQL is fun when geeks help others. And remember, the order that we specify the select clauses is different from the execution order of those clauses. The from clause is the only clause required with the select. Consequently, it is the first clause that's executed in a query. Again, it collects the information about the table itself, the environment, the variable names, the variable types, the number of rows, and other important information. If specified, the into clause is used to create one or more macro variables, which we'll see in a later section in this tutorial. If specified, the on clause is then executed to subset rows of data based upon the condition specified, and any rows that aren't satisfied by the condition are discarded. Should a where clause be specified, it is then executed. The where clause is used to subset rows of data based on the conditions specified, and rows, once again, just like the on clause, that are not satisfied by the condition are discarded. If specified, the group by clause is then executed. The group by clause takes the rows that were subset with the where clause and group based upon some common values in the column specified in the group by clause. If specified, the having clause is then executed. The having clause applies the conditions to the grouped rows specified in the group by clause, and any grouped rows that aren't satisfied by the condition are discarded. Then the select statement is executed. It's the first thing we specify, but next to last statement that gets executed. Essentially, the select statement specifies what columns we want to select or use in our query, or what columns we want to dynamically create in our query. And if specified, the last clause that's executed is the order by clause. Its purpose is to sort the rows of data in either ascending, which is the default, or descending order for viewing on output or for processing on output. So this table shows the execution order of all the select clauses. Now, why is this important? Because if you understand the order of the clauses, not just the order you specify the select clauses, but the execution order of the clauses, I believe that you will write better and more efficient queries. We then turned our attention to the join types using a Venn diagram, the inner join or intersect highlighted with the teal or cyan. We then looked at the left join where the intersect is collected, plus the preservation of all the unmatched rows from the left table. Then the right table, the intersect data is collected, plus all the unmatched rows from the right table. And finally, the full join construct, where the intersect information is collected, plus the preservation of all the unmatched rows from the left table, and the preservation of all the unmatched rows from the right table. We then looked at how to emulate using SQL first dot, last dot, and between processing. The first observation in each by group is selected with the min function. It uses subquery techniques. The last observation in each by group is selected with the max function. The between observations in each by group is selected with the having clause logic. For example, the min function with the title, our group by variable. The last by group processing uses the max function, ordering it by the categorical variable rating. The between by group processing uses the group by and the having clauses to be able to collect the between by group rows. The nearest neighbor processing, since PROC SQL performs operations row by row. Nearest neighbor processing identifies content that is close to one another. The data step is a marvelous tool to be able to achieve nearest neighbor processing, using lag, lead functions, etc. to be able to perform nearest neighbor processing. But if you're an SQL user or an SQL shop, PROC SQL does not support the use of the lag and lead functions, and consequently produces error messages. So I wanted to show you a way, you decide if this is worth exploring further, but a way to emulate nearest neighbor processing using output delivery system ODS output statement to number a data set or a table with row numbers, and then be able to process that through select logic, going backward one or more rows to be able to collect lagged rows or nearest neighbor data, or go forward one or more rows to look at the leads. Let's now learn about PROC SQL join algorithms and execution plans. Users supply the names of the tables along with the join conditions. The SQL optimizer will determine which join algorithm to use. The available join algorithms with PROC SQL include nested loop, sort merge, index, and hash. We're going to look at each one of these individually. A nested loop join algorithm may be selected by the SQL optimizer when processing small tables of data. One table is considerably smaller than the other table. The join condition does not contain an equality condition, and a sort merge, index, and hash join have been eliminated from consideration. A sort merge join algorithm may be selected by the SQL optimizer when processing small to medium-sized tables of data. A step loop, index, and hash join have been eliminated from consideration. An index join algorithm may be selected by the SQL optimizer when it is determined that using an existing simple or composite index will improve the performance of the join relation. A step loop, sort merge, and hash join algorithm have been eliminated from consideration. A hash join algorithm may be selected by the SQL optimizer when sufficient or real memory is available to the process to store at least the smaller of the table into memory. The mem size equal and or buffer size equal options can also be set optimally. A step loop, sort merge, and index join algorithm have been eliminated from consideration. How do you go about overriding the SQL optimizer? Well, there's magic options magic equals 101 instructs the SQL optimizer to select the nested loop join algorithm. There's also a magic equals 102. Magic equals 102 instructs the SQL optimizer to select the sort merge join algorithm. And there's also a magic equals 103. When specified, it instructs the SQL optimizer to select the hash join algorithm. Let's take a look at the magic equals 101. We're asking SAS optimizer to choose the sequential loop join. So we're going to specify magic equals 101 on the PROC SQL statement, and then whatever join construct that we've specified. In our example here, we have an intersect. The results from specifying the magic equals 101 option will appear on the SAS log. The log will show a note. In this case, the PROC SQL planner chooses sequential loop join. Taking a look at the magic equals 102 option for merge join, we can specify on the PROC SQL statement magic equals 102, essentially telling the optimizer that this is the join algorithm we want to be chosen. Once the code is executed, we can look at the log, and we should see, by specifying magic equals 102, that the PROC SQL planner chooses the merge. The third magic option is 103 for hash join. When we specify magic equals 103 on the PROC SQL statement, essentially what we're doing is we're telling the SAS optimizer to perform in memory the join algorithm, at least with the smaller of the tables. Once the code is executed, we can look at the SAS log and see what the results might be. In this case, when specifying magic equals 103, we're forcing the optimizer to choose a hash join. But the PROC SQL planner, by default, would have chose the merge join. But because we forced the issue by specifying magic equals 103, a merge join was transformed to a hash join. Now let's take a look at how can we look under the hood of SQL. In other words, see how our query or queries are processing. We can display the execution plan with the underscore method option. The underscore method option basically is going to display the hierarchy of query processing or an execution plan. The results will be automatically displayed on the log. For example, by specifying underscore method on the PROC SQL statement, we can specify our query, our select query in this case, and then we can examine how it performed by looking at the log. Now the underscore method is going to display one or more codes on the log. It will not display the descriptions that I am showing here, but it will display one or more of the codes. For example, SQX-CRTA for creating a table as a select, SQX-SLCT when a select statement or clause has been specified, or it might display SQX-JSL when a step loop join or Cartesian type of product was specified or selected by the optimizer. Or it might choose SQXJM, indicating that a merge join operation was selected by the optimizer. So these options, these codes itself, gives us the ability to inspect how our query is performing behind the scenes or under the hood. SQXJNDX indicates that an index join operation was performed. SQXJSL JHSH indicates that a hash join operation was selected and performed by the optimizer. SQX sort indicates that a sort operation was selected and performed by the optimizer. SQX src indicates the source rows from the table that were selected. SQX FIL indicates that there was row filtration occurring in the query itself. SQX SUMG indicates that an aggregate or summary stats were executed because of a group by clause. And SQX SUMN indicates that summary statistics were performed or executed when no group by clause was specified. These are all codes that could appear on your log. So if you'd like to see what your query's doing, how it's performing, what type of resources it's using, specify _method on the PROC SQL statement, and then whatever query that you have. In our example here, we are specifying an intersect or an inner join construct. And then when you execute this code with the _method option, your log will show one or more of these codes. And the codes will give you an indication and a better understanding of what your query did and how the optimizer and what the optimizer did and how the optimizer performed using your query. It's a very helpful way to better understand what's happening with queries. Now, these codes are a bit difficult to remember, so that's why I provided the brief description to help you recall what each code means. Now, there's another very useful thing that I like to have all SAS users be aware of. It's called options message level equal I. It's a SAS system option that allows helpful notes about index usage, sort utilities, and merge processing to be displayed on the SAS log. It has nothing to do with just SQL. It can be used or specified anywhere in the SAS system. But option message level equal I is going to give you informative messages that you would not ordinarily see on the SAS log. It's extremely helpful in better understanding what your queries, what your programs are doing with the available resources that you have. The log will show in an info message, for example, any index that was chosen by the optimizer to speed up processing. So in this case, in lieu of sequential processing, by turning on options message level equal I, we see that the optimizer found and used an index called rating. So what I'd like to do is give you a summary of takeaways for this chapter, or this section that we covered. Again, the available join algorithms are nested loop, sort merge, index, and hash with PROC SQL. So the optimizer has choices. We can override the SQL optimizer by forcing it to use or specify or execute a sequential loop join with magic equals 101, or magic equals 102 for a merge join, or magic equals 103 for a hash join. Now, don't put this override in production code. Let the optimizer make the choice. But during testing, it can be very useful. We also looked at how we can explore and better understand what's happening under the hood of our queries, so we can better explain, better understand what type of resources are being used, what kind of Join algorithms are being executed by the optimizer, etc. And it's done with an underscore method option. The underscore method option gives us one or more codes that are going to be displayed on the SAS log. These can be extremely helpful in helping you better understand what your query and the SQL optimizer has done with the query that you've executed. And again, I list these codes with a brief description of what each code means. Now you may see one, two, or more of these codes. So become familiar with the underscore method option and it would be very helpful. Then we finally looked at message level equal I SAS system option, giving us the ability to display helpful notes about index usage, sort utilities, and merge processing on the SAS log. We're now going to learn about fuzzy matching techniques using PROC SQL. We have an additional two tables that I'm going to look at and show you in the examples in this section. The movies with messy data consists of 31 rows or observations and 6 columns or variables. And it does have some issues with the data. I purposely added issues with the data itself. And you'll see by looking at the data that there's misspellings, there's incorrect rating types, there's some invalid movie titles, some duplicates, and things like this. Then we have another table, actors with messy data. This table contains 15 rows or observations and 3 columns or variables. It too has been purposely added some bad data to this table, misspellings, incorrect movie types, missing values, duplicates, things of this nature. Matching with common keys. Today's data exists in many forms, including data sets, RDBMSs, tables, spreadsheets, CSVs, etc. It involves matching 2 or more data sources to create a combined file. Using a common and reliable identifier or key, 2 or more data sets can be matched, merged, or joined. With our movies table and actors table, we have a key, title in both tables. In order to match or merge or join these 2 tables together, we're going to use the key. If the key is reliable, consistent, we should have very little problems in joining or merging these tables. But what happens when a shared and reliable key between data sources is non-existent, inexact, or unreliable? This can make the entire matching process more complicated and problematic. Consequently, Steve Sloan and I have put together 6 steps to successful fuzzy matching. Step 1. Remove the extraneous characters, such as quotes, single quotes, or double quotes, ampersands, dashes, question marks, things of this nature. Anything that really doesn't serve a purpose or a real important purpose. Step 2. Put all the characters in your search arguments in uppercase notation and remove leading blanks. Now these steps that we're showing here are useful. You can opt to avoid these steps by cleaning the data, performing data cleaning, or you can use some of these techniques with the fuzzy matching to improve the process of merging or joining tables of data when the keys are not that reliable. Step 3. Remove extraneous words that might not appear in different databases when matching company names, such as Inc., Ltd., LLC, CO, Corp., .com, company, corporation, division, etc. Anything that will cause a matching process to fail, try to remove the differences between the different data sources. Step 4. Handle numeric and character zip codes. Differentiate between US and Canadian zip codes because they are different. And include leading zeros when matching. Step 5. Choose a standard for addresses, such as street or ST, avenue or AV, road or RD, court or CT, lane or LN, etc. Consistency helps the join or merge or matching process immensely. Step 6. Match the names, addresses, company names, and other fields using SoundX, SPEEDUS, CompLev, and CompGED functions. If you specify them in this order, processing speeds can be improved. A side-by-side comparison of each one of these fuzzy matching techniques. SoundX essentially is an algorithm that matches words that sound alike, hence the name phonetic match. It ignores case, embedded blanks, and punctuations. It works best with English-sounding names. It assigns essentially a code to each letter and word. The SPEEDUS function translates a word into a smallest distance value. It returns a non-negative value. An exact match, when it occurs, returns a value of 0. The matching process can be controlled using the SPEEDUS function. The third technique is using the CompLev. It's a function in the base SAS system. It computes what's known as a Levenshtein edit distance, or LEV score, returning the number of operations that were performed to make one key's value match another key's value. An exact match returns a value of 0, and it too, the matching process can be controlled. The last fuzzy matching technique is CompGED. It's also a function. It computes what's known as a generalized edit distance, or GED score. The lower the GED score, the better the match, typically. An exact match returns a value of 0. And once again, the matching process can be controlled. So let's start by looking at the SoundX for phonetic matching. The SoundX algorithm matches strings or data on words that sound alike. SoundX is nothing new. It was invented and patented by Margaret Odell and Robert Russell in 1918 and 1922, respectively, to help match surnames that sound alike. Now that's over 100 years. It adheres to the following rules. It ignores case, in other words, case insensitive. It ignores embedded blanks and punctuations. The biggest problem or deficiency in using the SoundX is it's best in finding English-sounding names only. So how does the SoundX algorithm work? SAS determines whether a name or a variable's contents sound alike by converting each word to a code. The value assigned to the code consists of the first letter in the word followed by one or more digits. Vowels such as A, E, I, O, and U, along with the letters H, W, Y, and non-alphabetical characters, do not receive a coded value and are consequently ignored. Words with double letters, such as double T's, are assigned a single value for both letters. For example, deriving the SoundX algorithm codes, letters B, P, F, and V receive a value of 1. The letters C, S, G, J, K, Q, X, and Z receive a value of 2. The letters D and T receive a value of 3. The letter L, when encountered, receives a value of 4. The letters M and N, when encountered, receive a value of 5. And the letter R, when encountered, receives a value of 6. Let's examine how the movie title, Rocky, is assigned a coded value of R22. R has a value of 6, but it is retained as R. O is ignored. C is assigned a value of 2. K is assigned a value of 2, and Y is ignored. The general syntax is variable equals SoundX, some value. Looking at this example, we see that we have an SQL query with a where clause that says title equals asterisk, that represents sounds like Michael, in quotes, a character string. It's going to derive the code behind the scenes and evaluate other titles that sound like Michael. The result is it's going to extract or display the movies with the title Michael and Mikkel. Because the AE in Michael or the EA in Mikkel are vowels, they are ignored. So they sound alike. Now let's turn our attention to the SPDIS or spelling distance function. It contains 2 arguments. It evaluates possible matching scenarios by translating a keyword into a query containing the smallest distance value. The SPDIS function returns a non-negative value. A SPDIS value of 0 is returned when the query and arguments match exactly. Users are also able to control the matching process by specifying spelling distance values, for example, in increments of 10, 10, 20, 30, etc. The general syntax for the SPDIS function is SPDIS, and since it's a function, argument 1, argument 2, query, keyword. Now let's look at an example of how the SPDIS function can be used in an SQL query. We're going to use the SPDIS function. Argument 1 is going to be the variable title. Argument 2 is going to be the value we are looking for, Michael. We're going to assign it to a value called SPDIS value. And then in our where clause, we're going to say where SPDIS value is greater than or equal to 0. Code this, but I want you to see the different values itself on this output. We see that there are all sorts in the last column, the SPDIS value column, we see that there's all sorts of numbers. The larger the number, the less likely the match. The smaller the value for the SPDIS value, there's a better chance that that's a match. So for example, if you look at 7 for Michael or Mikkel, that looks like it's a match. So it's consistent with the SoundX algorithm as well. Let's take a look at another example. In this example, we're going to look at SPDIS title for Michael, assign it to SPDIS value. where speedest value is less than or equal to 20. So now instead of looking at all these large values, we're going to constrain the value to 20 or less. The hope is that we're going to find a greater likelihood of matches here. And we see in the results that Michael, as well as Michael receives 0, Michael receives 7, falls within 20. Now you decide whether or not these are matches. We can use these functions and these fuzzy matching techniques to help us in our matching process. The next function we're going to look at in the fuzzy matching area is CompLev. CompLev stands for Levenshtein edit distance. The CompLev function provides an indication on how close two strings are, with one exception. The CompLev function returns the number of operations that have been performed to make string 1 match string 2. The more operations that are performed, the less likely that there's a match. Consequently, the lower the number of operations, the better the match. For example, 0 equals best match, 1 next best match, etc. The general syntax for the CompLev function is CompLev, string 1 and string 2, which are required, and an optional cutoff value and modifier. Again, the required arguments are string 1 and string 2, which essentially specify a character variable, constant, or expression. Now we're going to look at what the optional arguments are. The cutoff value specifies a numeric variable, constant, or expression. The modifier specifies a value, when specified, that alters the action of the CompLev function. Valid modifier values include I, L, N, and colon. I for ignore case, L for remove leading blanks, N ignoring quotation marks around string 1 or string 2, and colon truncate the longer value of string 1 or string 2 to the length of the shorter value. In this first example of CompLev, we're going to select the movie title from the movies table, rating, length, and category, creating a new variable, a derived variable called CompLev number. And at that point, what we're going to do is we're going to say order by, in ascending order, movie title, where the title is not equal to missing. So what we want to do is we want to look at the category variable, looking for the value drama. The last column, the CompLev number, is going to indicate how many operations were performed in order to make the string 1 equal to string 2. And once again, Michael or Michael has a very low value here, 0 or 6. In this next CompLev example, we're going to look at, once again, using the CompLev, the variable category for the keyword drama, assign the number of operations to the CompLev number, and now we're going to say CompLev number is less than or equal to 1, and then order the results by the movie title in ascending order. Now that we have a better understanding of how the CompLev function works and the types of values it provides, we can control it with our where clause or our on clause, depending upon whether or not we have a join operation going on. So it gives us the ability to control what type of output, what type of matches we want or don't want. In this case, since we specified in comp-lev number less than or equal to 1, we see that Casablanca with drama, Forrest Gump with drama, Michael with drama. Notice there's a spelling error on the second Forrest Gump. It has two M's. It has a value of 1, meaning that one operation was performed to make it match the single value drama. So this gives you a better idea and understanding of what's happening behind the scenes. The next function and the last fuzzy matching function we'll look at is the comp-GED function. It's a technique that works by computing what's known as a generalized edit distance or GED score when comparing two strings. The GED score acts as a measure of dissimilarity between two strings. The higher the GED score, the less likely the two strings match. Consequently, users should seek the lowest derived GED score for the greatest likelihood of a match. The general syntax for the comp-GED function is very similar to the comp-lev function. The two required arguments, string 1 and string 2, and then two optional arguments, cutoff value and modifier. Again, the required arguments, string 1 and string 2, specifies a character variable, constant, or expression. And the optional arguments for cutoff value and modifier adhere to the same syntax and the same values as the comp-lev. The cutoff value specifies a numeric variable, constant, or expression. When specified, the modifier specifies a value that alters the action of the comp-GED function. Valid modifier values are I for ignore case, L for remove leading blanks, N for ignore quotation marks, or colon truncate the longer value of string 1 or string 2 to the shorter value. Just so we see the full complement of all the different fuzzy matching techniques with SQL, this first example is going to show how the comp-GED function is used in a join process, in this case an inner join process, or an intersect. What we're doing here is we're actually going to retain the movie title from the movies table, the title of the movie from the actors table, the movie rating category, the leading actor, and then we're going to evaluate from the movies table the title against the actors table and the title, and store that value as a comp-GED score. And then we're going to order the results in ascending order by the movie title. And what we see here, since we didn't constrain or limit the number or the size of the values in the comp-GED score, we're seeing the whole litany of values here, from 0 to 400 and everything in between. Now you might wonder, ghost in mixed case versus ghost in uppercase, why does it have a value of 400? Well, we'll see how we can fix that a little later. Comp-GED function example 2. Again, I want to show you how you can perform a match merge or a join process with SQL. In this case, we're going to retain the value for the title in movies, the title in actors, rating category, leading actor, and then we want to derive the comp-GED score from both tables, movies with messy data and actors with messy data, where the title is not equal to missing and the calculated comp-GED score is less than 100, less than or equal to 100. What is calculated? Where did that come from? Well, calculated is a keyword that allows us to take advantage of derived variables that we're creating on the select. If you recall in lesson 1, I talked about the order of execution. If we don't specify the calculated keyword prior to the comp-GED score, the value will not be available in our where. So the calculated allows us to take advantage of derived values. And in this case, less than or equal to 100, we now have a more likely matches here between the movie titles and the actors' titles. In our third CompGED example, we're going to continue with the same code, basically, that does a match merge or a join process. But we're going to take a look at a modifier, the I modifier. And basically, what we want to be able to do is we want to be able to ignore case. That's what the I modifier does. If specified, it allows us to ignore the case. So case is no longer important, whether it's uppercase or lowercase or mixed case, as long as it's spelled the same. And then we want to display subset where the calculated CompGED score is less than or equal to 100, and then display the results in ascending order by movie title. And now we see ghost, and I highlighted that, ghost in mixed case versus ghost in the actors table, all uppercase, is now being treated as the same. Notice its CompGED score is 0. Prior to this, it was 400. Now it's 0. This gives us the ability to use one or more of those modifiers to process our data so that we don't get mismatches when it comes to perfectly spelled data, but just case problems or case issues. In our fourth and last CompGED function example, I'm going to show you same code, except for now the modifier has, in quotes, INL. What this is going to do is it's going to remove or ignore the case. It's going to essentially remove the leading blanks. And N, it's going to process where the quotes around the data values themselves, going to remove those. And we want to basically display the CompGED scores where it's less than or equal to 100 in ascending order by movie title. And now what we have here is we have less than 100. Now we have a list of those movie titles that probably, can't say certainly, but probably are a match. So you can play with the values. Maybe 100 is still too large, but you can reduce that to 20 or 50 or whatever you want. So what are the summary of takeaways in this lesson? The 6 steps to successful fuzzy matching. Step 1, remove extraneous characters that are not necessary for performing the match or the lookup or the join. Step 2, put all characters in uppercase notation and remove leading blanks. Or use the modifier that ignores the different cases. Step 3, remove extraneous words that might not appear in different databases when matching, that could be causing problems with the matching process. Step 4, handle numeric and character zip codes, differentiate between US and Canadian zip codes because they are different, and include leading zeros when matching. Step 5, choose a standard for addresses, cities, states, etc. And step 6, now that you have been introduced to some of the fuzzy matching techniques, perhaps use the Soundex, the Speedus, the CompLev, and or the CompGED to help you in the matching, lookup, or join process. And once again, the soundex, it matches words that sound alike. It ignores case, embedded blanks, and punctuation. It works best, though, with English-sounding names only. It essentially assigns a code to each letter or word. Speedest function translates a word into a smallest distance value, returns non-negative values, and exact match returns a value of 0, but the beauty is the matching process can be controlled. The comp-left function, if you decide to use this, computes what's known as a Levenstein edit distance score, returning the number of operations that were performed to allow string 1 to be equal to string 2. An exact match returns a value of 0, and once again the matching process can be controlled. The comp-GED function computes a generalized edit distance, or GED score. The lower the GED score, the better the match. An exact match returns a value of 0, and just like the previous speedest and comp-lev, the matching process can be controlled. Let's now learn how to construct logic scenarios with case expressions in PROC SQL. Two case expression constructs exist. A simple form, known as simple case expression, which supports one or more when, then, else conditions, compares an expression against multiple values, specifies an equality check only, and does not support and or between Boolean expressions. And a more sophisticated, robust form of the case expression known as the searched case expression. It supports one or more when, then, else conditions, permits the use of comparison operators, and supports the use of and, or, and not between Boolean expressions. Case expressions serve as an embedded construct to reclassify or regroup data into separate and unique categories or groups. They're very handy. Case expressions look something like this. The keyword case with an optional column name with one or more when, then conditions and an optional else. Every case must end with an end keyword, and you have the ability to assign a user-defined column name from the results. Specifying the column name in a simple case expression reduces the number of keystrokes required to be entered. For example, in our select query, we're selecting title and category, and then have an embedded case expression on rating when G, then assign a value of general audience, when PG, assign a value of greater than 13 audience, else assign greater than or equal to 17 audience. To the derived column, the new column called my rating. So the end result of this is going to be title, category, and my rating. A search case expression provides more robustness by supporting one or more when-then condition and comparison and logical operators. For example, we can specify in our select query title and category, and then our embedded case expression. When rating equals G, then assign a value of general audience to my rating. When rating equals PG, then assign greater than 13 audience to my rating. Else, assign greater than or equal to 17 audience to my rating. Now this gives us the ability to use not only equality scenarios, but other comparison operators, less than, greater than, not equal, etc. A search case expression permits two or more columns to be combined with Boolean operators. or in this case, logical operators. In our select query, we're specifying title, category, along with our case expression, when rating equals G, and category equals adventure, then assign general audience adventure to my rating, else assign other. So it gives us the ability to create compound conditions using logical operators as well as comparison operators. So search case expressions are more robust, more powerful, and give us all the ingredients to be able to construct our logic scenarios intelligently. Now, what are some summary of takeaways? In this section, we looked at logic and case expressions. There's two forms of case expression constructs. A simple case expression, which is limited, but it's simple and it reduces the amount of keystrokes. The problem is that it does not support anything but equality checks, and it does not support and or between Boolean expressions. And a search case expression, which is more robust and powerful and gives the users the ability to support one or more when-then conditions, when-then-else conditions, permits the use of comparison operators, along with supporting the use of and, or, and not between Boolean expressions. Let's now look at the rules, strategies, and usage of indexes in the SAS system. What are the benefits of an index? The way an index is designed, it may be able to improve performance by providing faster and efficient access to data subsets, by returning rows in ascending value order for by-group processing without using the sort procedure. There's two types of indexes in the SAS system. A simple index consisting of a single column, where the index name is the same name as the column. The second type of index is a composite index, representing two or more columns. The index itself is assigned a unique user-defined name. An index file contains entries organized hierarchically. Entries are connected by pointers. The entries themselves are organized in ascending value order. Entries contain the following information: a unique value and one or more unique observations. This is referred to as the record identifier, or RID. Something that the SAS system does for us is it basically reclaims unused or used space from an index. One index file exists per SAS data file or table. It possesses the same name as the data file itself, and it's stored in the same SAS library as its data file. An index represents a separate entity and has a unique member type of index. A binary search is performed on the index file itself. Positioning the index to the first qualified value that matches the where clause expression using pointers. Visually, entries representing the index file look something like this slide. This table shows unique values for the movie rating G, PG, PG-13, and R, and the record identifier or RID, representing the observation itself. So for example, on observation 21, the movie rating G. For observations 2, 9, 14, 15, 18, and 19, the movie ratings for PG. Indexes are not free. They do cost resources because an index must be maintained by the SAS system. An index is updated each time a table is modified, for example, a new row, deleted row, or updated row. The SQL optimizer ultimately determines whether an index will be used. Index usage. An index is triggered with where clause processing. Keep in mind though, sequential access may be just as efficient when a subset is large. Avoid defining more indexes than are needed. Avoid constructing indexes when the data file page count from the contents procedure is less than 3. And the optimizer may use a defined index, whether it's simple or composite, when the subset is 15% or less of the population. For example, the page count from PROC contents, when you specify the details option, you'll see the number of dataset page size. So this is a very useful piece of information. So become familiar with the results from either PROC contents or PROC datasets. This is very useful metadata information. Now, how do you go about selecting columns that's going to be used in an index? Select columns that are used in queries containing where clause processing. The columns used in an index should select the fewest observations. When creating a composite index, where there's 2 or more columns, the first column should be the most discriminating. The second column should be the next most discriminating, and so on and so forth. One way of understanding the distribution of data, let's take for example the variable category, the movie category, is to use PROC Freq. So if we delve into the details of the data with PROC Freq and produce a tables category, we see that we have an alphabetical list of the category values, their frequency, the percent of that frequency, cumulative frequency, and cumulative percent. Category by itself, with the exception of one value, falls below the 15% rule. How does the movie rating variable hold? If we see the distribution of data for the rating variable in the movies table, we see that we have G, PG, PG-13, and R-rated movies. We look at the frequency and then the percent. 3 out of the 4 values exceed the 15% rule. Consequently, the optimizer may be less inclined to use the movie rating variable or index when processing a dataset. Now, how about the distribution on 2 columns? What would that look like? Well, we can continue looking at and using PROC Freq on the movies dataset by specifying tables and the most discriminating variable category, followed by the next most discriminating variable, let's say rating, in a 2-way table. We're going to suppress the row and the column information, and we see by looking at this table that we are beneath or below the 15% threshold, which is a good thing. So how do you go about creating an index, in particular a simple index? An index references one or more columns in a table, such as the movie category or rating. The name given to a simple index is the same as the column that the index is being created for. Take, for example, to create an index with SQL, we use the create index statement. So if we want to create an index on the variable category, we can say create index category on movies. Now this does require that we have exclusive access and use of the data set itself in order to create an index. How about creating a composite index? The name given to a composite index must be different than the individual column names. Following the syntax from our simple index, we can use SQL to create an index. In this case, we want to create an index on the movies table or data set for category as our primary variable and our secondary variable rating. So we're going to have to create a user-assigned index name, and the name we're going to assign it is cat rate. How about creating a unique composite index, where the duplicate values in an index are prevented from occurring by specifying the unique keyword? Using the code we created to create our composite index, we can use that same code and just add create unique index. And let's say we want to create a different composite index for title and rating. Title being the primary variable and rating being the secondary variable. The index we're going to create is called title rate. As we mentioned in section 1, turning on messages. By specifying the message level equal I option, helpful notes describing index usage, sort utilities, and merge processing are displayed on the SAS log. This is very handy because this is the only way that I'm aware that we can see and determine what index has been selected by the optimizer. If we don't specify options message level equal I, and this goes with anywhere in the SAS system, whether we're using SQL or a data step or anything, if we specify options message level equal I, this is the only way we can determine and have it displayed on the SAS log which index, if any, the optimizer has chosen for us. And we see by specifying options message level equal I that we have an info message appearing on the SAS log that says index rating selected for where clause optimization. What this means is, in lieu of sequential processing, we're going to dynamically access the contents of the data based upon the index key. How can we further test this to evaluate the index? We have something known as an IDX where equals dataset option. This IDX where dataset option ignores sequential processing altogether, thereby letting the optimizer to select which index is best. So if you're unsure which index to use, perhaps choosing IDX where equals yes, it will automatically turn off sequential processing. The optimizer will have no choice but to choose one of the best indexes for the query itself. And to provide detailed information as to which index was chosen, we specify the options message level equal I system option. We have another way to specify and evaluate indexes. By specifying the IDX where equals dataset option, SAS can be made to ignore sequential processing. So what we're going to do is we're also going to request timing statistics, CPO, I/O, the amount of memory, by specifying on our option statement message level equal I That will give us information about which index was chosen by the optimizer, assuming one or more exist, and full steimer, which gives us a complete listing of performance statistics, resource statistics, and things like this that will be displayed on the SAS log. And we're going to specify IDX where equals yes, meaning let the optimizer choose which index is best to satisfy the processing of the query. We also have another data set option. It's called IDX name equals to evaluate indexes. Just like the IDX where equals, SAS can be made to ignore sequential processing, thereby letting us to select which index to use. Now, both the IDX where equals and the IDX name equals dataset options are well and good. For testing purposes, I would refrain from specifying them in production code. I'm a fan of letting the optimizer choose which is the best for everything. Whether it's a join algorithm, whether it's an index or sequential processing, I don't like to force the SAS system to use one method over another, unless I'm testing and evaluating. So just keep that in mind. And some general index housekeeping. When a column containing an index is dropped from a table or data set, then the index is also automatically dropped. This housekeeping operation is automatically performed by the SAS system. There are times when an index is no longer wanted or needed. In those cases, we may want to remove an index. We can do this easily with the SAS system, in this case PROC SQL. We can specify drop index, and then assuming we know the name of the index we want. If you're unsure of the index name, you can always do a PROC contents or a PROC datasets, and it will tell you not only the dataset names, but the index names, the view names, and other things. But we can display drop index, cat rate from movies. Again, this requires exclusive use and access of the dataset in the library itself. So what are the summary of takeaways from this section? First, there's two types of indexes. A simple index consisting of a single column. The index name is the same name as the column. The second type of index is a composite index, representing two or more columns or variables in the dataset or table. The index itself is assigned a unique user-defined name. Anatomy of an index. One index file exists per SAS data file or table. It possesses the same name as the SAS data file or table. It's stored in the same SAS library as its data file, whether it's work, SAS user, or some user-assigned libref. An index also represents a separate entity and has a member type, a distinct member type of index. And a binary search is performed against the index file, positioning the index to the first qualified value that matches the where clause expression using pointers. What are some rules for index usage? Indexes are triggered with the where clause. Keep in mind sequential access may be just as efficient when processing or subsetting large data sets. Avoid defining more indexes than are needed. Avoid constructing indexes when the data file page count from the contents procedure is less than 3. And the optimizer may use an index when the subset is 15% or less of the population. How do we go about selecting columns? Select columns that are used in queries containing where clause processing. the columns used in an index should select the fewest observations. And finally, when creating a composite index, the first column or variable should be the most discriminating, the second column should be the next most discriminating, and so on and so forth. Let's now explore the PROC SQL macro interface. There's two types of macro variables, a single value or aggregate, and a value list or essentially an array of values. Single value or aggregate macro variables can be created in PROC SQL by specifying the into clause. In this example, we're selecting the movie title and rating from the movies table or data set, and we're creating two macro variables with the into clause, which is an optional clause, using the colon, and then we're going to name the macro variable. I'll call it M title and then M rating. A where clause is specified to control which row is selected in the assignment of macro variable values. Now this is important because in the absence of a where clause, the first row or rows will automatically populate the macro variables. The where clause gives some control over what row or observations are going to be used to populate your macro variables. So in this case, we're carrying on with the same example from the previous example, selecting title, rating, creating two macro variables, M title and M rating, where upcase rating is either PG or PG-13. Multiple macro variables can be created by specifying a range of macro variables in the into clause. In this case, we see the into clause M title 1 dash, that's not a minus sign, M title 3, M rating 1 dash M rating 3. In this case, without a where clause, we're going to be taking the first three observations and populating the contents of the movie title and movie rating for each one of those macro variables that we're creating. And the percent put statements just list out on the log what the values are. Macro variables can be created from system variables using the into clause for reporting purposes and whatnot. So for example, if we wanted to select the system date and the system time and assign a format of date 11 and time 5 and store the results into two macro variables, the macro execution date and macro execution time, we can do this by just selecting one observation. The first observation is going to give us this valuable information that comes from the system date and system time. It wouldn't be important to select all observations. We only need one observation to do this. And then we can use that content in our reporting, etc. We also have the ability to create what's known as a value list macro variable. We're going to construct a tilde delimited value macro variable containing values of a single column into one macro variable. So in this case, we're going to continue using the into clause. We're going to read in the data for the movie title, storing the results out for PG rated movie titles, separated by tilde. The separated by keyword with the into clause allows us to create an array of values. Each distinct value is separated with a tilde. The reason why a tilde was specified is a tilde is found very infrequently in the world of data. So it's a good separator. Continuing with this theme, we want to select values for searching purposes with the %scan function. And we're going to accomplish this with the where clause. So for example, using that same example we just did, select title into :M title separated by tilde, where rating equals PG. We're going to use the %scan in a %let statement, and we're going to assign the value for the third word for the macro variable we created, $M title, looking for the third word, in other words, the second after the second tilde, and we're going to store the results in scan bar. It's a new macro variable that's going to contain the name of the movie of the third word in this list of values. Then we're going to use in our where clause, where title equals $scan bar. So $scan bar is going to resolve to whatever the third word is. So what are some of the summary of takeaways in this section? There's two types of macro variables: a single value or aggregate, and a value list representing an array of values. The macro variables that are created with the PROC SQL into clause is magnificent. It gives us power to be able to use these content of the macro variables anywhere in the SAS system. In this last section, we're going to look into data-driven techniques. Programming languages are often classified by their basic features into one of the programming paradigms. Three popular programming paradigms are in use today. Procedural programming. Procedural programming is represented by blocks of code being organized logically by function, such as data input, data processing or manipulation, and data/results. Object-oriented programming is represented by a combination of functionality or behaviors and data attributes hidden inside an object, which can then be arranged into what's known as classes. The third, data-driven programming, is represented by data essentially controlling the flow of execution in a program. So what is data-driven programming? Unlike procedural programming languages and object-oriented programming, data-driven programming involves decisions and processes that are controlled by the data itself. Why design data-driven programs? Data controls the flow of a data-driven program. It has the ability to write other programs. It also allows us to minimize hard coding approaches, which transcends into being easier to maintain. And the hope is to reduce programming efforts along with costs, providing reusability and cost savings. Let's take a look at a data-driven program example. A data-driven approach will be illustrated to create multiple Excel files. Excel is the world's #1 software product, and we're going to see how we can do this with the SQL procedure and the macro language. Triggering by calling a macro containing macro code, PROC SQL, the ODS Excel destination, and PROC Freak to send output and results to Excel. Step 1. We're going to use PROC SQL with the into clause. PROC SQL with the into clause is used to dynamically create single value and valueless macro variables. In this example, this first part, step 1 of this example, shows that we are essentially creating a macro, calling it multi-Excel files, selecting the count of distinct ratings. So we have 4 unique ratings in the movies data set, G, PG, PG-13, and R. And then we're going to store that into a macro variable called mRating_count. We're then going to select the distinct rating, the values themselves, storing the results into a macro called mRating_list separated by tilde. We're going to order the results in ascending order by rating. Step 2. Both macro variables are processed with a PROC freq and an iterative macro %do statement, a %scan function, and where equals dataset option. Essentially, we're going to iterate through this, however many unique values there are for the rating variable. In our case, there's 4. So we're going to iterate through this do loop 4 times. This macro do loop is going to structure through, and for each movie rating, it's going to create an Excel file. And it's going to name the Excel file. For example, the first pass through is going to name it G_list_report.xlsx. It's going to generate a PROC freq. It's going to do this 4 times for each distinct movie rating. The results are 4 separate Excel files, one for G-rated movies, another for PG-rated movies, a third for PG-13 movies, and a fourth for R-rated movies. What we've taken advantage of is using the ODS Excel destination along with PROC freq and the capabilities of the macro language to create a reusable tool with SQL to create our macro variables, to create a very handy way to dynamically create Excel files. So what are the summary of takeaways I'd like for you to know from this section? What is data-driven programming? Unlike procedural programming languages and object-oriented programming, data-driven programming involves decisions and processes that are controlled by data. Why design data-driven programming programs? Data controls the flow of a data-driven program. So it behooves us to have clean data or reliable data. It also has the ability to write other programs and to minimize hard coding approaches, resulting in something that's easier to maintain. Also, reducing programming efforts along with costs, providing reusability and a cost savings to the organization itself. In conclusion, we explored many powerful PROC SQL programming techniques. Techniques like first dot, last dot, between, and nearest neighbor processing. We then looked at join algorithms and execution plans. Join algorithms like the step loop, sort merge, index, and hash join algorithms, and execution plans underscore method and message level equals I. We looked at fuzzy matching programming techniques, including SoundX, SpeedUs, CompLev, and CompGED. We then looked at logic scenarios with case expressions and the 2 types of case expressions, simple case expressions and search case expressions. We then turned our attention to index rules, strategies, and usage, creating 2 types of indexes, simple and composite indexes. We looked at the PROC SQL macro interface to create 2 types of macro variables using the SQL into clause, the single value and the value list. Finally, we looked at data-driven programming techniques using PROC SQL, the macro language, PROC freq, and ODS Excel. A little self-promotion. I've written PROC SQL Beyond the Basics Using SAS, the 3rd edition for SAS Press, and it contains intermediate and advanced PROC SQL content, including fuzzy matching and data-driven programming techniques. I'd like to thank each and every one of you for viewing this video tutorial. And I'd also like to thank Lisa Mendez, the SAS Global Forum 2020 Chair, her EC, SAS Institute, and all the users everywhere. Thank you.